Hi everyone, welcome back after lunch. So hopefully you had a bit of a break over lunch. Well done, by the way, for this morning. That was a really interesting for us to. Sorry, I'm just going to turn my fan on. It's really hot in here. Hopefully this doesn't disrupt things. Last time I didn't. It got very hot, and I was in the middle of teaching and nearly fell unconscious. And whilst it may be acceptable for you to fall unconscious when I'm teaching, it's perhaps not for me. But yeah, it was really interesting for us to see you approach a sort of more free-form challenge, and there's going to be more of this kind of stuff as we go through, because ultimately you're working towards your projects and thinking about what your projects are going to be, where there are no right answers. You are going to be pioneering and exploring brand new data, new models that you've not seen before. I think there was lots of learning that we managed to get out of that. Hopefully, so just to say, there's going to be a hackathon in 2 weeks, part of the natural language processing module, where you'll have basically a bit like what you did this morning, a bit more sort of structured, but you'll basically have the whole day to explore some data sets. So it'll be interesting to see how you explore that. But some really good stuff coming out this morning. I think with a bit more time, actually, you've created some really wonderful things. So really good, and I saw some fantastic things bouncing around the room. So well done, everyone. So that's machine learning done as a module. Or is it? Because as we move into natural language processing, actually, we're going to be touching on a lot of those concepts that we talked about in the machine learning module, particularly around neural networks. Yes, you're delighted to revisit neural networks. I just know it. But looking at the way in which we use these kind of AI approaches in order to look at text data, free text data, and exploring those issues. So this is a relatively short module compared to the one you've just been through, and is a bit of a bolt-on, which will show you. And I mean, there's so much in natural language processing that we couldn't hope to cover it. But what we're trying to do is focus this module very much on, as ever with HSMA, on applied practical things that you can try for your own data, and hopefully things that you'll find useful in your project work and beyond. So let's get cracking on our text adventure. So let's talk about natural language processing first. So natural language processing, commonly abbreviated to NLP. What do we mean by that? Well, it's basically an area of analysis, of modeling, of AI, in which we are focused on the way in which human language and computers interact with each other. And broadly speaking, as I say, it's a huge area. It's got a lot of visibility in recent years, particularly over the last couple of years, because of things like ChatGPT, etc. But it really is a huge. There's so much to natural language processing. But broadly, we can divide natural language processing into two kind of broad camps. So there's something called natural language understanding, or NLU, which is basically trying to look at ways in which we can understand the intended meaning of text. And there's natural language generation, which uses various methods to try to get machines to generate text that is as natural as possible. So when you think of GPT, which is the underlying model that is powering the ChatGPT interface that you're so familiar with now, that's an example of a natural language generation model. And indeed, in the historically, there was something known as there's something known as the Turing test, named after Alan Turing. And it was seen for many years as kind of the gold standard of trying to assess whether a machine exhibited real intelligence. And the way it did that was by essentially trying to fool a human being into thinking they were talking to another human being and not a machine. So natural language generation was kind of seen as a big thing for, if we can teach machines to generate language convincingly and have a conversation with them, then have we created true intelligence. Having said all that, we are very much going to be focusing, as fascinating as the world of natural language generation is, its uses for the kind of work that you'll be doing, looking specifically at operational research, looking at operational decision making, is less useful than this natural language understanding. So we're going to be very much focusing on the course on this side of things. Having said that, a number of the approaches and the methods that underpin natural language understanding also underpin a lot of the things that underpin the natural language generation side. So we will be touching on things that actually expose how some of things like GPT work as well. So there is a lot of crossover. But in terms of the applications, we're very much focused on the natural language understanding side of things. So why are we teaching you this? Why is natural language processing and specifically the kind of natural language understanding side of it useful for what we want to do? Well, basically it allows us at a fundamental level to try and extract information from free text data, and the NHS and policing organisations and social care have huge amounts of free text data that historically has been very difficult to tap into, and actually natural language understanding approaches allow us to tap into that and extract some information from that kind of data. And it allows us to do things like text classification, which is where we're trying to classify different types of text, different text into different types. So much as we looked at the machine learning module, we looked at classifying whether passengers on the Titanic survived or died, or whether patients who'd had a stroke were eligible for thrombolysis clot busting treatment. We can do the same thing with text. We can classify whether we think this text belongs to this class or to this class. And one of the most common uses of text classification is something known as sentiment analysis, which we're going to come on to next week, which is essentially where we are trying to automatically identify and classify the tone of a piece of text. Is it positive in tone? Is it negative? Is it neutral? We can also look at that. And so we'll specifically be looking at sentiment analysis next week. However, the principles used for sentiment analysis, which are themselves, sentiment analysis is very useful for all sorts of reasons for the kinds of work you'll be doing, but those same principles apply even if you're trying to classify in a different way. So if you're not interested in tone or sentiment, you're interested in classifying text in a different way, then you can do that. Indeed, we had a previous HSMA project, I can't remember if it was last year or the year before, that was looking at automatically classifying text data from social media posts to try and classify whether they contained mention or implicit mention of illicit drug use. And so that's, again, just a text classification problem, the same approach as you would take for sentiment analysis. So hopefully that'll help you think about things that you might be able to do with that kind of approach. We can also do things like pick out key types of information from our text. So named entity recognition, again, something we're going to touch on next week. We're going to be looking at how we can extract specific named entities, names of things and stuff and people and places automatically using AI-based approaches from our free text. And also we can kind of combine NLP and kind of vanilla machine learning by trying to extract data that's in free text to see if we can use that information to help our machine learning models. And we've had HSMA projects that have done that before. To look at an example, we had one that was trying to look at GP patient notes. Can we extract information from GP patient notes that would allow us to identify data that could then be fed into a machine learning model to predict whether we think the patient's likely to be imminently admitted to hospital, for example. So, as I say, in this module, we're going to look at a few different approaches. The main ones we're going to look at will be sentiment analysis, which is a variant of text classification. So we'll be looking at text classification and named entity recognition. Those are the two big things that we're going to be looking at, and we're going to be looking at both of those next week. But today we're also going to be looking at some other things as we introduce some of the concepts that underpin so much of natural language processing too. So let's start with looking at a really nice and simple natural language processing thing that we can do that actually, while simple, can be really useful. And this also has the benefit that in showing you how to do this, we can also show you along the way lots of concepts that are important for these more complex things that we'll get into next week. So we saw in many of the previous modules on the program that whenever you approach any kind of modeling problem, really good first step is to try and get a feel for your data or system first. So, you know, discrete event simulation, what's the first thing you do? You go and build a process map. You understand how the system works. Geographic modeling, you're having a look at your geographic maps, looking at where the demand is, where whatever it is that you're looking at, where your locations are. With the machine learning, you're looking at your data. The first thing we told you to do in every notebook was, right, have a look at the data first, get a feel for what the data looks like. And so natural language processing is no different. And indeed, a first good step is to get a feel for your text data. And obviously, if you're dealing with large amounts of data, you probably don't want to be reading through 50,000 separate documents. We want some way in which we can visualize that meaningfully, just to get that sort of feel, that taste for what our text data looks like. And so a really nice way of doing that is to generate a word cloud, and word clouds probably you're all, or most of you will be familiar with. You may even generated them using various pieces of software yourself. Just really simple visualizations that basically show the most common words in a piece of text, and words that occur more frequently appear larger. And they're really simple but effective visualizations to get a sense about the kind of things that are being talked about in some text. So what we're going to do first of all today is to use a nice little Python package called wordcloud, which is nicely named given it generates word clouds, in order to generate a word cloud based on some text within Python. And before we do that, and before we see how it's done, because actually it's very easy to use this package, in order to get your data, to process your data into the format we need to do various pre-processing. And we talked a lot about pre-processing for data this morning for machine learning, but natural language processing is no different. But a lot of the pre-processing stuff that you do for natural language processing is very different, because fundamentally we've got a different kind of data. We've got a text data, and that requires a different approach. So the first thing I'm going to talk about, which is really useful whenever we're doing any or most approaches to natural language processing, is a concept known as stop words. So a lot of natural language processing tasks, text classification, things like sentiment analysis, generating word clouds, not all, sometimes this doesn't apply to everything, but for a lot of applications, we're usually not interested in the kinds of common words that we find in text that are used basically across all text. So words like and your and he and she and because and all that kind of stuff isn't usually very useful if we're trying to sort of classify our text. Sometimes it is. So sometimes the presence of words like that help us understand context, and we'll come back to that more in the named entity recognition stuff. But certainly for a word cloud that we're generating now, we don't really want to see the word the appearing very large. It doesn't really help us in any way. That's quite meaningless to us. So these kind of common words that are used across all text, we probably want to filter them out before we do this kind of analysis. And in natural language processing, these kind of words are referred to as stop words. Now, when we generate a word cloud, we want to get rid of those words first, as I say, because they're not going to be of interest to us. The good news is that there are lots of built-in lists of such stop words that we can use that allow us to automatically say get rid of these things. And different packages that we use come with their own sets of stop words, basically. Another important concept whenever you're doing any natural language processing is the concept of tokenization. So tokenization is basically something in natural language processing where you are splitting up your text into some form of component parts, and those component parts are referred to as tokens. So the process is tokenization, and that creates these tokens. Normally, tokenization in natural language processing means splitting up your text into individual words, but it doesn't have to be words. Sometimes it can be individual characters, sometimes it could be things like morphemes, which are a bit like syllables, but semantic versions of syllables. So it could be parts of words that are tokenized. Most commonly, though, you split up into individual words, and that's the kinds of thing we'll be doing in this module. There are different ways in which we can do that, in which we can break up our various text. It's also important to note, and you'll see this in the example this afternoon, that tokens also include punctuation. Punctuation is part of your text. They are symbolic characters and therefore count as text. Often we don't need punctuation, and so we tend to remove it, and you'll see in a minute how we can do that. But here's an example of tokenization. So probably this is a very common sentence here. Dan is a great teacher, something you probably say and write all the time. If we were to tokenize that into individual words, which is the kind of the default for most tokenization algorithms, that would split into these tokens here. Dan is a great teacher, but you'll notice that the exclamation mark next to teacher is indeed included in the token for teacher. And that's really important to note, that the vast majority of tokenization methods will do that by default. Another really important thing to consider whenever you're doing any natural language processing is and you may have sort of come across this in your general Python training. Remember we said that in Python, a string is essentially just a list of characters. That's how Python interprets a string of text. And that means that equivalency, in terms of checking whether one string of text matches another, is very dependent on the characters used. And the characters used depend on the particular case that is used in some text. So the case of some text matters when we're doing natural language processing. So if we have the string cheese with a capital C and cheese with a lowercase c, and even a string cheese where we've got various combinations of upper and lowercase, they are different strings. Python will interpret those things differently. Now, sometimes that might be important. Sometimes we may want to treat those things differently and treat those as different words. But for things like word clouds, for things like sentiment analysis, we typically want to consider all of these three variations on the word cheese here as being the word cheese. We know we want to treat that as somebody's written the word cheese, basically. So we want to treat them the same way. And so because we don't care about the case, we want to treat everything as equal. Typically what we do is in natural language processing, we convert everything to lowercase. So case is basically taken out of the equation. You can do the opposite. You can actually make everything uppercase if you wanted to, but conventionally you don't. Conventionally, you put everything into lowercase. I'm also going to talk a little bit about a kind of weird little thing called a translation table, which, as far as I can recall, you are only going to use today, but you might come across them elsewhere, so it's worth flagging up. And they're a bit weird, so if I don't talk about this now, you won't understand what else is going on for the word clouds. So the string library in Python, as you might imagine, has lots of really useful methods that we can tap into to allow us to work with strings, and therefore becomes quite useful when we're dealing with text-based modeling, which is what natural language processing is. One of those methods in the string library of Python is a method called makeTrans, which allows you to create a mapping table that basically maps one character to another in some text. And there's basically three key ways you can use it. You can just pass it one input, and that one input is basically then a dictionary, and it says every time you see the character D, turn it into the character S, for example. Okay, or you can call it and pass in two inputs, and then basically those two inputs have to be two strings of equal length, and it basically maps the ith character of the first string to the ith character of the second string. So you could say pass in the strings A, B, C, and D, E, F, and that would say, okay, translate all characters A into D's, translate B's into E's, and C's into F's. And that would be how you'd set that up. But you can also do this thing where you pass in three inputs, which is the same as where you pass in two inputs, except the third input represents any characters that you want to be removed. You don't want to translate them, you want them gone from your text. So why am I telling you all this? Well, hopefully it's starting to sink in. This might be quite useful if we had some characters, say, to remove, like, for example, punctuation, which we just talked about. It's a nice, easy way to allow us to get rid of punctuation from our text data. Okay, so those are some of the key concepts. So we just gloss over those again. So stop words, which are common words found across most texts that we probably are not interested in, certainly not for a word cloud. The concept of tokenization, which is where we split our text down into individual tokens, usually individual words with the various punctuation attached to it. The fact that case in text matters when we're dealing with natural language processing, so we have to be aware of that. And these things called translation tables, which basically allow us to get rid or translate certain characters from within our text. So, armed with that information, we're going to have a look now at the word cloud package and how this is used. So basically this is how we're going to generate a word cloud from some text using the word cloud package. Basically, as you probably would imagine, if I'd have said what would be the first step, you'd shout back at me, Dan, and of course we always import the necessary libraries first. That's all we ever do when we as our first step for a Python code, and you'd be right, and indeed it's written right there to confirm that. Then we're going to read in the text from which we want to create our word cloud. So we'll read that in. We'll set up our stop words, those words that we basically want to ignore in our analysis. We'll then tokenize them, so split them up into individual words, albeit with the punctuation still attached. Then we'll purge the tokens of their punctuation. We'll make all the tokens lowercase, and then we'll bung everything back together. So we'll join up these tokens, which are now lowercase and they've been stripped of their punctuation. We'll join them back together as though it's a single string of text, and then we'll basically apply the word cloud package to that single string. And then finally we'll use matplotlib, our good old trusty friend, to display the word cloud that's been generated using the word cloud package. So actually it's not, and this is basically what you'll do every time. It's a fairly straightforward process, and hopefully you'll see the code now is actually fairly straightforward to do this. So I'm going to walk you through the code very quickly. You'll have a chance to look at this properly in a moment in the exercise, but hopefully this will all make nice sense to you. So the file we're going to look at is wordcloudexample.py. It's in your lecture examples, and we're going to be generating a word cloud from bttf reviews.txt, which you probably would guess is some Back to the Future reviews that I've taken off the Internet Movie Database. What else could I use to demonstrate the word cloud package? Now, the way I'm going to demonstrate this is a little bit different to the way you've seen before. I'm actually going to run this code bit by bit. So it's going to be in a .py file. It won't be in a Jupyter notebook, but I'm going to run a selection of lines each time. And I'm going to do that. You can do that yourself in your own code by right-clicking and select Run in Interactive Window, and then Run Selection Line in Interactive Window. And you can see you can just run each bit of the code in a standard Python script bit by bit. And it's quite a useful thing to do. I should also point out it does have a shortcut where you can push Shift and Enter. I'm not blaming VS Code. That does not work on my machine. It does something. It does not work properly. So maybe it works for you. If so, great. I'm delighted for you. Doesn't work for me. So if you wonder why I have to keep right-clicking, that's why. Just to also flag up, we're going to be using, for this and indeed for all of the exercises you'll be doing today, we're going to be using the NLP basics environment that we supplied with the repository. So let me come out of this, and I forgot I hid my bar, so let me go into VS Code. I'll zoom in a bit here so it's a bit easier to read. You may have noticed, gosh damn, that your VS Code looks incredibly neon all of a sudden. Indeed it does. I have installed a new theme that I tried to install last year and it wasn't working properly, but it is now working. So if you think you're looking at VS Code and think this doesn't look 80s enough, well, there's a theme for you. And indeed, of course, that was going to be the theme I installed. So just be aware from now on, you're going to see a lot of neon in my code examples. Okay, so first thing we're going to do is to import our libraries. Remember, we said we need to do that. We have to make sure wordcloud is installed, which it will be if we're using our NLP basics environment, which we are. And so we import that. We import the string library from Python and also matplotlib in the same way we've done before. So I'm just going to run those imports first of all. Right click, run an interactive window down here, and then run selection line in interactive window, and you'll see it'll just run that bit of the code once it's connected. There we go. So it's just run that, nothing else so far. A bit like clicking a cell in Python. It's basically how it works. Let me just zoom out a tiny bit so I can actually, some of that's a bit hidden now. There we go. Okay. So the next thing I'm going to do, I said I'd read in the text that I want to create a word cloud from, and that's what I'm doing here. I use my open file statement with a with statement, as we've seen before. What you probably haven't seen before is I'm just calling this read method on the file. Basically, read is not something you tend to use very often, except in natural language processing, because it basically just says, read everything, just give me everything in one big mass. But actually, for natural language processing, that can often be quite useful. So that's basically what we're doing here. It just says, read the whole thing in and store it in full text. So that's what I'm going to do here. And in fact, if I then in the console type in full text and run that, let me just, sorry, let me get rid of that, minimize there. So you can see there against full text now stores this string is a single string of text that contains all of these reviews, these 5 reviews, all in one big mass. Okay. So then we've got our stop words. We need to set up our stop words. The word cloud package comes with its own set of stop words here, and so this basically just assigns it. We cast it as a set. Don't worry about the details of that. I've put more details in the comments, but just know this is basically what you would do. So let me run that, and in fact then we can have a look at the stop words. I type stop words and run that. And you can see, indeed, they are these kind of words. So these are the words that we want to ignore. These are the kinds of common words that we see across all text. This is the stuff that we're going to say we don't want, we're not interested in for our word cloud. Okay, and of course you can add your own as well. There may be other things you want to ignore. Then we're going to tokenize the text. So we're going to split it up into individual words, but remember that any punctuation will still be attached to it. We'll have a look at that after. So all we need to do on that, if we call the .split method on any piece of text, any string within Python, that will automatically tokenize. So that it's as easy as that. That's how we tokenize text. So if I run that, we'll then store that in tokens. Let's have a look at tokens here. And you can see now we've got a list, and these are all the individual words in those 5 reviews, all in order. And you can see, if I can find an example, there we go. You can see there are the punctuation is still attached to the words where there is punctuation. Okay, so we've read in our text, we've set up our stop words. The stop words will still be in our text, so we haven't done anything with it. We've just said these are our stop words. And we've tokenized them. So we split them up into individual tokens. We're now going to do that thing where we set up a translation table. And again, we're going to use this 3 input way of doing it. We don't need the first two inputs, so we're just going to put a blank string, an empty string for both of those. The thing we need is this third input, which is, remember, anything we want it to remove. And so we basically want it to remove punctuation. Now, you could sit there and write out all the different punctuation marks that you can think of, but fortunately there's a shortcut, because in the string library, it actually has its own list of punctuation. And in fact, if I type in string.punctuation, you can see that list. Here is the list of punctuation symbols that appear within the string library. So basically, this says, any of those you see in my text, get rid of them. Replace them with nothingness. So that's what that'll do. This translation table here, we're just setting up the table itself. We're not applying it just yet. So this just sets up that when I call and tell you to use the punctuation mapping table, that's what I want you to do. I want you to take the text I give you and get rid of the punctuation. So let me run that line of code there. Then we're actually now going to use that, and so we can use the translate method on an individual token to apply a translation table, and we've just set up a translation table up here, so we can just say token dot. We're going to use a list comprehension here. So remember, list comprehensions easiest read from the middle. So this says for every token in tokens, which is our list of tokens. So for each token in the tokens, give me back the token translated using the punctuation mapping table that I've set up above. So in other words, give me the token, but without any punctuation, if there is any. And then I'll store the result of that in token stripped of punctuation. So let me run that. And then hopefully we'll see token stripped of punctuation, run that. Now, as I scroll up, you will see that there is no punctuation in any of those tokens. But what you can see is that we've still got those blasted capital letters. So we're going to have to do something about that, because we want everything lowercase. Fortunately, that's really easy to do too. We can convert any string into a lowercase just by calling the .lower method on a string object. And of course, our tokens are all string objects. They're just strings. So again, we can use a list comprehension. So again, start from the middle. This basically says for each token in our token stripped of punctuation, so this lot that we've just created, give me back the token but made lowercase. And so if I run this line of code here, and then we have a look at lower tokens, you can see that's exactly what's happened. We've got no capital letters. And now we've got a list of tokens called lower tokens that have no punctuation and they're all lowercase. Now all we need to do is put everything back together into one single string. Another really neat feature with Python strings is you can join them back up, and you can join strings together really easily using the handily named join method. And so what this line of code is saying here is that I want you to take the space character, this empty character here, and I want you to use that to join up all of these strings here, which is this lot, the lowercase tokens. And so, as you can imagine, and then we'll store that in this join string. So we'll end up with a single string of text again, just as we had at the start. Except this time, if we have a look at join string, you'll see we've got all lowercase and no capital letters. Sorry, all lowercase and no punctuation. Okay, we're ready for our word cloud. So here's how we can use our word cloud package that we've imported. So I'm going to create a word cloud. I've imagined it should be called it word cloud, and I'm going to create a new word cloud object. Things I'm passing in here are the size in pixels, so width and height, the background color that will form the background to the word cloud, the stop words if we want any. You don't have to. This is an optional argument. You don't have to put that in. If you want to include stop words, you can. But obviously, we said we don't want stop words, and we set up our list of stop words up here. There, we called it stop words. So we'll pass that in. And then we've got this thing here called minimum font size, which sounds obvious, and indeed it is doing what you think it is. The minimum font size is 20. But it's actually a little bit more interesting than that. The way it actually works is that it will exclude any words from the word cloud that would appear smaller than size font, whatever we've put in, so font size 20 here. In other words, they would be excluded because they are too uncommon. So you can kind of use the minimum font size as a proxy for your threshold for inclusion into the word cloud. So the larger the minimum font size, the fewer words will make the cut into the word cloud. So you'll only be looking at the most common words. The lower that is, your word cloud will include less common words as well, albeit smaller. Okay, so that sets up the word cloud as a word cloud. All we then have to, I haven't actually run that. That would help. I knew I'd forget to do one of them. There we go. All we need now to do, we've created the word cloud. All we have to do is plot it. And fortunately, these little matplotlib commands will do just that. We have to sort of tinker with matplotlib a little bit to get it working. We basically say, I don't want any axes on our plot because it wouldn't make sense. It's not a graph. And we use this thing called imshow, which basically allows us to show an image. And so all we're doing here is setting up the size of the image, turning the axes off, and telling it to show an image. And the image we want to show is the word cloud we created up here. And I'm also going to save it as a .png as well. So let's run this, and you should see appear, once I run it, a word cloud. So let me just make this a little larger. There we go. So this is the, a bit smaller because it's not fitting now. This is the word cloud that we've created of our 5 Back to the Future reviews. So we've got words like movie, back, time, future, all words that I would probably expect to see as fairly common words within some reviews of Back to the Future. And it really is as easy as that. You can generate a word cloud that easily using Python for any piece of text that you have. I can't bring up my panel. There we go. Let's go back to the slides. Okay, so I've done enough talking. Sammy, any questions that have cropped up in the chat?
Yep, so just a couple of things, not too much. Sorry,
You've muted
sorry,
yourself.
audio didn't seem too great there. I seem to get some feedback. Hopefully that's fixed now. So going back to the translation tables, there was a question about whether that has to be just a single character or whether we can use multiple characters. So I think that was slide 9.
Thank you. So the way that would work is it would it only does single characters, but there will be a way to do multiple characters. I don't know offhand. Google it.
Cool.
I suspect it's in. There might be a more efficient way to do it than a translation table, is what I'm thinking. But you can probably do it that way. Yeah.
Yeah. The next one was there's a lot of people who are very interested in knowing what the theme was, the neon theme.
Oh,
so
right.
that's proving very popular.
I can't remember offhand. I'll get you the link because I posted it to the team. Yes, I'll post it. It's a very nice thing.
Fantastic. There was one question about whether the colors mean anything. Chris has just tried this out and he's run it twice, and the colors are different each time. So I think the impression I get is the colors don't mean anything in the word cloud. Yeah.
No, they don't.
Fabulous. Next one that's come through. So there's an interesting question about the applicability more generally of NLP to healthcare and the analysis of free text notes. And Ian's raised that a lot of the time this data isn't available to analysts due to the sensitivity of it and how potentially powerful that data could be. And just a more general kind of broad question to anyone in the group, whether they're aware of scenarios where it's been possible to kind of work around this. Is it possible in some way to perhaps apply NLP to data sets without actually fully getting sight of them and only seeing the end results? But also then there's some discussion about how you'd actually validate that it's working correctly in that instance. So tricky one.
I wouldn't. I haven't. I'll be honest. I haven't come across that issue before. A lot of what people have done in HSMA projects before have been things like patient survey data that they've collected, and rather than pay large sums of money for people to sit down and manually read through thousands of patient surveys, to build an AI that will automatically do that, and identify things people are talking about, the whether people are talking positively, negatively, that kind of thing, or things like accessing patient notes, things like that. Yeah, I mean, if you have got restrictions that you can't see that kind of thing, that yeah, I mean, I wouldn't ever advise modeling blind. It's one thing if you had, so some of you might be on a project that's like a collaborative project with a number of you, and to avoid IG issues between organizations, you might say, okay, well, I can't show you our data, but can you build that bit of the the software, and I can then apply it to our data. That's fine. But yeah, don't do that. I mean, I would also there are huge amounts of publicly available open free text data as well, and you'll see some of that actually in the hackathon in a couple of weeks, because that's exactly what you're going to be doing. But perhaps not now, but obviously in the old days when Twitter used to be Twitter, and a bit different to how it is now, it used to have a very nice open API, and you could tap into Twitter data and things like that. Other social networks have their own things, so there is public data available. It depends what you're trying to do, but yeah, you do need. It's like anything; you need that data if you're working with it. Really.
Fabulous. Two small remaining questions. In the code, is there any reason to not do the lower casing before splitting into tokens? That was one of the questions raised.
Anyways, well, it's more. I'm trying to think. There probably is a reason. You kind of want. The thing is, what you want at each stage here, you're kind of setting up different components that you might use in different ways. So you have your raw string of text that represents your original data. Then you've kind of got it split up into that raw text, but split up into tokens. Then you've got a version of it with no punctuation. Then you've got a version of it with, and it might be that you then want to use that text for another NLP approach, where the case does the case does matter, and you want to keep that. So you can easily then access those tokens. So you could do it either way, yeah. But that's probably the approach I would take this way.
Brilliant. And the final one is just on the code again. There's a few instances showing up where you can see like time travel and Christopher Lloyd are being identified as sort of phrases and appearing together rather than as single words. And there was just a question about how that, if we know how it makes that decision on what to have like that.
Excellent question. We're coming back to that, so I'm not going to answer that. So we're coming on to that later. But yes, well spotted. That is a thing, and we will be coming back to that later on this afternoon.
I think in that case that's everything.
Okay, cool. Right. In which case, I'll stop talking and we'll move on to the exercise. So you can have. I'm going to give you. Let's go until 3 because I've gone over a little bit. I'm just going to see if we can claw back a bit of time. I'll see how well you get on. Take a break in there as well at some point. So until 3 o'clock, you can have a go at this task here. Well, 2 tasks. So you work in your groups. So you've just seen the word cloud code that we've used. You've got access to that as well. First task, I want you to take a copy of that and then adapt that. And I want you to adapt it to remove these particular words that I flagged up, because these words, movie, film, back, future, obviously are coming up. One seems to be coming up a lot. I don't know why, but it is. And they're probably, we've decided they're not that useful for us. That's not really telling us much information. So I want you to remove them from your word cloud analysis. And you can do that however you like, trying to make your solution as elegant as possible. So again, you have free-form creativity on this, but try and future-proof it as well, so that if I then turn around and said, oh, I don't want that word in there either, you'd be ready for me and could easily do that. Then the second bit of the task, I want you to try out your new word cloud generating skills by creating another word cloud on text of your choosing. It can be any text you like. And once you've generated your word cloud, try refining it. Try taking out words like you did above. try tweaking the way in which it's visualized, different colors, sizes, different proxy limits on the words that are coming through, and then post it once you've done that in your group Slack channel, and Sammy's going to award some PSG points for the nicest word clouds. So that's an exciting thing on this Tuesday afternoon. Okay, I will stop talking and I'll open up the breakout room. See you at 3. Hi everyone, welcome back. So, I think it's safe to say you all had quite a bit of fun with that. Seemed to be quite a nice little exercise. A really nice word clouds I'm starting to see appear. Really interesting ones. Sammy's actually going to announce her favourites just before the next exercise. When I get to the end of this little teaching section, because there's so many good ones coming in. She's losing track, so she's going to go back through and have a look at those. But if you haven't had a chance to check out some of those, they look absolutely amazing. And those that didn't spot the link that I posted, that's a really nice link to the documentation. When you sort of look up the documentation, it's a bit bare bones, but it does have a link to the project homepage. And if you go to the project homepage, sorry, this one here. Am I sharing? I forgot to share. Sorry, I'm saying this one here. If you go to the project homepage, then it actually takes you to the GitHub repository. The GitHub repository has lots of examples. The beautiful parrot one is there. Little Alice in Wonderland one. And you'll also see there, and it's got the example code for how these work. If you have a look at the examples folder in the repository, it's got loads and loads of different ones. There's ones around stormtroopers. It's got some really nice stuff there. Yeah, do check that out, because there's some really cool things you can do with that. Okay, so we're going to move on to the next bit now. So that was word clouds, and hopefully you can see that's a really nice, easy way in which you can generate these word clouds. But hopefully you got used to some of these concepts too, which are going to be really important as we move forward with the natural language processing theme. So the next thing we're going to talk about is a really important concept within natural language processing, and that is the concept of vectorization. And this is fundamental to the way in which a lot of the approaches we're going to be using work. You may have already sort of thought about this a little bit, but obviously I mentioned when we covered neural networks a couple of weeks ago, and explained how they work, and said you're basically feeding through numbers, and it's doing weighted sums on those numbers, and the weights get adjusted. So effectively, you've just got this sort of these complex mathematical operations going on. It spits out a number the other side. Well, how do you deal with that if your data is not numbers but is text? And obviously in the kind of machine learning examples we looked at, we turn everything into numbers. If the text represents categories, then we one hot encode. If it's Boolean, we put a 0 or 1. But for text data, it's the text that's of interest. So there's no point in getting rid of the text. We need the text to be represented in some way, because that's the thing we're interested in. And this isn't just a problem with neural networks. Computers at a fundamental level have to deal in numbers. Any computer algorithm ultimately needs to work. They're very advanced calculators, essentially. So we have to, whenever we're doing analysis like this, we need to be able to perform mathematical operations on the data that we're feeding through. But we can't do that with words. We can't perform mathematical operations out of the box on words. So what do? Well, the answer is vectorization. So vectorization basically just simply describes the process in which we turn text data into numeric data, and specifically, as the name might imply, a vector of numbers. Okay, so we're taking raw text and we turn it into a vector containing numbers. And our vectors that we obtain through vectorization are of fixed size, which means that all of our data becomes of the same length. And that's important because, as we touched on in the neural networks sessions, I think we touched on it. If we didn't, I'm telling you now. Anything that gets fed through a neural network has to be the same size and shape. You cannot feed through differently sized, differently shaped things within the same data. Now, of course, you're probably thinking, well, hang on, how's that going to work for text data? We'll come back to all that next week. But essentially, our vectors will represent, they will be fixed size numerical representations of our text. Now, there's lots and lots of different ways in which you can vectorize text. And the thing that you create with these are known as word embeddings, essentially. Now, we're going to look today at a really simple approach, a vectorization approach that you can use and that is quite fun and useful to use, and we'll show you the broad concept of vectorization. When we come on to do sorry, I'm so conscious of that word cloud where it picked up I was mostly saying and indeed I am. So the most common approaches that we're going to be using for things like name density recognition and sentiment analysis and all that kind of stuff that we'll do next week. The vectorization approaches that we use for that will be slightly different to what we're showing here. This is a very simple approach, and you'll end up using a slightly more sophisticated approach. You won't need to sort of code it all from scratch. It'll do a lot of the hard work for you. But the principle is the same, and so this is a nice, easy introduction to what it means to vectorize, and it gives you some sense about how you can turn text into numbers, basically. Okay, but this is essentially what we're talking about. Talking about turning words, lists of characters, ultimately, and symbols, punctuation, because we may need those depending on what we're doing in our natural language processing, into numerical representations. So the word Dan might become the number 1, for example. Is might become the number 37, you know, that kind of thing. So we're turning words into numbers. That's what vectorization is. So the approach we're going to look at this afternoon to demonstrate a type of vectorization is an approach known as bag of words, and it's probably the simplest of all the vectorization approaches. It has a lot of shortcomings, which we'll come back to, which I'm sure will become obvious as I describe this. But basically, in bag of words, we count the number of times a word occurs within a document. I'll come back to a document in a moment. It doesn't capture anything about the order of the words or the structure of the sentence or anything like that, and that's why it's called a bag of words. It's just a jumble of these words that represent a bag of numbers, essentially, that represent the frequencies of words across our documents. Now, there are limitations of that, and we'll come back to why that can cause problems, the fact that it's not capturing word order or structure, but we'll come back to that. But for now, just understand that's why it's called a bag of words. Now, I keep saying the word document. So in natural language processing, a document refers to something very specific. It basically means a single record of text. Now, what that record is will obviously vary depending on what your particular problem is. But it's much like in our machine learning examples, say with the Titanic data, we had individual passengers. For the stroke data, we had individual stroke patients. They are our separate records. In natural language processing, a document is one of those records, basically. So a document, depending on what we're doing, could be like a single patient's questionnaire answers, or it might be that the individual answers on a questionnaire are separate documents. Depends what we're trying to do. It might be a particular movie review is a document, or the GP notes for a patient. Again, it depends what you're doing, but it's whatever a record is that makes sense for your particular problem. And we can actually use bag of words, and is actually commonly used to look at similarities. How similar are two pieces of text? And that can be useful to help us classify documents in certain ways, or even do things like clustering similar words together, or similar pieces of text together, which is known as topic modeling, where you're saying these, and that's an example of unsupervised learning, where you're saying these kinds of things tend to be talking about the same kind of thing, so they must be related in some way. Now, I would point out there are more advanced ways of doing that. We won't cover on the course, but as I say, Bag of Words will give you a sort of introduction, a flavour of what it means to vectorize text, and we'll apply it to do a little bit of similarity analysis. I should point out, you probably guess this is AI generated. I don't know what. It's certainly no human language that I've ever seen that this is supposedly a bag of words, and I can only imagine that ChatGPT is indeed an alien. Okay, so let's have a look at an example of Bag of Words in action. Let's imagine that we've got these 3 reviews, 3 documents, essentially, for our purposes, for HSMA. We've got the first review saying HSMA is a brilliant program, it really is. Second review, HSMA embraces the 80s. Third review, I thought the program is 280s. I don't know who this person is. We've probably got rid of them already. So these are our 3 reviews. Now, if we wanted to vectorize these reviews, then using Bag of Words, what we would do is we'd need an entry for every unique word across every document. So across our 3 documents, our 3 reviews. And we'll basically count how many times each word appears in each review. Okay, so here we've got our 3 documents on as separate rows, and then we've got all of the unique words. So in the first review, that's all of them. HSMA is a brilliant program. It really is. Sorry, HSMA is a brilliant program. Now, of course, we've already got is there, so we don't need to put that again. Second one, HSMA, we've already got that, but this introduces the word embraces, so we'll need that, a column for that. We haven't had before, so we need a column for that. 80s, we need a column for that. And then in the third review, we've got I thought too as being words that haven't come up before, so we'll need separate columns for those too. And basically all we then do, a Bag of Words, will then just go through and say, okay, how many times does the word HSMA come up in review 1? How many times in review 2? How many times in review 3, etc. And then the same with the word is, the same with the word a, the same with the word brilliant, etc. And what it then does is it then turns that row, essentially, into a vector, and it uses those frequencies, those word frequencies, as the vector. So review 1 would become the vector 1, 2, 1, 1, 1, 1, 1, 1, 0, 0, 0, etc. And that now becomes our numerical representation of the review HSMA is a brilliant program, it really is. Okay, so it turns that text data into numeric data of fixed size, which means that we can then do machine learning on it. We can feed it through a neural network. We can whatever we want to do with that text data. So how do we implement a Bag of Words in Python? Well, there's actually quite a few different ways of doing it, but the one I'm going to show you is using something known as the Count Vectorizer class, which comes in the scikit-learn package, which you will be familiar with from Module 4. So basically what the Count Vectorizer does is it tokenizes your text, so it splits it up, it counts the instances of each token for you, and then it puts that in a matrix. That's exactly what we need for a Bag of Words, so it seems like a good choice. And indeed, Count Vectorizer is a popular choice if you want to do a Bag of Words vectorization. Now, an extra little thing that Count Vectorizer does for us, which is quite handy, is by default it'll make all words lowercase and it'll strip out the punctuation when it tokenizes, which saves us needing to do that separately. And usually that's what we want. It is worth flagging up, though, that it does that because depending on your... I mean, you probably wouldn't use Bag of Words if you're doing this for a real application anyway, but if you were, for whatever reason, and you didn't want things made lowercase and or your punctuation stripped, be aware Count Vectorizer will do that automatically, so you need to think about a different way to do it. The other thing to flag up, which is a little bit, again, probably not a major issue, but it's worth knowing, is that it will ignore any single character words, so words like a or I. Normally that isn't a problem because most of those are stop words, if not all of them. But just be aware that it does that by default. So here's the steps that we're going to follow if we want to vectorize using bag of words using the count vectorizer. We will create a count vectorizer object, so an instance of the count vectorizer class. We're then going to call the fit transform method of the count vectorizer, and that will tokenize the text for us. It'll clean it up, remove punctuation, make everything lowercase, as I mentioned. It'll create something known as the vocabulary. Basically, that's just the set of unique words across all documents, excluding our single character words. So this here, these column names, that's your vocabulary, essentially. It'll then count each word in the vocabulary in each document, and it'll then return a matrix representing the per document counts. And then what we're going to do then after is then stuff that into a pandas data frame to make it a bit easier for us to visualize. You will see the actual count vectorizer is a single line of code that is incredibly simple. So it's very, very easy to do this. Most of the code that I'm going to show you is actually doing the little bits around it. And in fact, not even that isn't particularly complex. So let's have a look at the code. So I'm going to go over to, you've got a copy of this as well. It's a bow.example.py. So if I go over to VS Code, let's close those down. Close that one and that one. Let's put those in order so I can follow them. There we go. Right, so let's have a look at bow example. Let me close this off as well. First thing we'll do, import the packages. So I'm going to import the count vectorizer from scikit-learn, specifically from scikit-learn feature extraction and the text, a bit of that. I'm also going to import pandas as well. Then I'm going to set up my documents. Here in reality, you'd probably read these in, but here I've just hard-coded them into the code just to show how this works. So here I've got a list basically of 3 strings of text. Those are my 3 documents. I'll create a count vectorizer object, which is as easy as saying, give me a count vectorizer object and call it something. So I've called mine vectorizer. I'm then going to generate the bag of words. So this is how you generate the bag of words. This single line of code, you just call the fit transform method of your count vectorizer object, which I called vectorizer. So vectorizer.fit transform, and into that you pass in your documents, which is just my list up here. So pass in that will give me back a bag of words. It really is as simple as that. But to make this a bit easier to visualize, I'm going to create a pandas data frame so we can read this a little bit more easily. So I'll grab the column names, which remember will represent the words in our vocabulary, here by calling the get feature names out method of the vectorizer. So we can grab those column names, grab out the words in our vocabulary, which we'll use as our column names. And our rows will basically be the counts for each of those words for each document, just as we had in that table that I showed you. And then we can have a look at it once it's done that. So let me run this code. Sorry, where's the play button? There it is. Okay, this will take mere seconds to run once it's connected. There we go. So you see here are 3 reviews. I've printed them out along with their bag of words vectorized form. So HSMA is a brilliant program. It really is. Becomes 0, 1, 0, 1, 2, 1, 1, 1, 1, 0, 0, 0, etc. This one becomes that. This one becomes that. If we have a look at the pandas data frame, so if I bring up the BOWDF, have a look here. Let me move this out of the way. So we can have a look at the data frame here, and you can see, just as we had before in the example I showed you, we've got the unique words here. So 80s, brilliant, embraces, HSMA, is it program really the thought to, the frequencies in each document. So in the first review here, there was no mention of the 80s, but there was a mention of the word brilliant. So we get 0 and 1 for the first 2 elements, etc., etc. We can see that it's basically pulled out, done exactly what we think it should, and so we very easily can get our bag of words vectorization, and it literally is as simple as that to do so. Now, let me just move on to this bit. So you will have noticed that other than the caveat where I said it will remove single letter words, which tend to be stop words like I and A. It will, by default, the count vectorizer will keep any other stop words. And again, normally, we probably don't want them. The good news is that you can remove them really easily when you set up the count vectorizer object. You just set the stop words setting here, and you pass in as a string the language of the stop words you want to use. So this uses its own set of stop words, and you say, I want the English stop words, please. I want you to ignore all English stop words for the text I'm about to pass you. And literally, it's as easy as that. So if I run the example 2, which is exactly the same, the only difference is I've passed in the stop words here. I'll run that bit of code. Let me just, so I'm going to move this out of the way because it's getting in the way. Run that again. Okay, so you can see now the vectors are shorter because we've excluded stop words. And in fact, if we have a look at the BODIF, this time, here we go. So we can see this time we've got 80s brilliant embraces HSMA program really thought, whereas before we had things like is and it and the and to in there. They're stop words. We've got rid of those now. So our vectorizations of these reviews get simplified. Okay, so we've simplified our vectorizations here. Now, the next thing to sort of talk about is something that cropped up earlier in one of the questions, and I said I'd come back to it. So let's talk about this now. So in natural language processing, there is something known as an n-gram, and an n-gram is basically a sequence of characters, or more commonly of words, in text that are of length n elements, which sounds like a very precise but slightly confusing a definition of something. So what do we mean by that? Well, in text that we've got, we may often see, if we just talk about words, for example, but the same principle applies to characters, we would very often see, depending on the text we're looking at, certain combinations of words used next to each other. So if we got some text about the HSMA program, we would likely to see HSMA and program next to each other quite a lot. Lord of the Rings, we would commonly see together, or TV series in a review of a TV program. These are kind of patterns we would expect to see. And for example, if we've got other texts about HSMA, we might see Dan Chalk or Sammy Rosser come up quite a lot if people were talking, depending on what the documents were. So there will be certain combinations where it doesn't just make sense to just look at the word Dan, where it might, but we might also want to look for Dan Chalk, because it may not be that useful to see the word Dan separately to the word chalk, because if somebody's talking about chalk in HSMA, it's probably connected to Dan, for example. And similarly with program, it's probably connected to HSMA. And so it's useful to identify these kind of n-grams, because there'll often be these kind of sequences of words that will always go together, and they will differ depending on what your documents of interest are. Now, so far, we've only looked at what we call unigrams. So unigrams are single word sequences. So we've just looked at one word at a time. We've taken each word separately as a separate thing. But we can also look at things called bigrams, and bigrams are basically two-word sequences, so an n-gram where n is size 2, or trigrams where we've got three-word sequences. So in this example here, I've got the link to where this image is from, the cat in the hat. We'd look at essentially two words at a time. So we'd look at the cat, cat in the hat. So it's like, imagine like a sliding window, or gradually sliding across the text, and this time, instead of it just being enough of one word, we've expanded it out, so we're looking at two words at a time. And that can be quite useful. It can help us, depending on what we're trying to do, it can help us provide more information, a bit more context, a bit more useful information for our vectorization, and depending on what we're then using our vectorization for, it might then help with our machine learning or whatever we're trying to do with it. And the good news is that if we're using a bag of words and we're using the count vectorizer to do that, we can very easily specify that we want n-grams that are larger than 1. And so BOW example .3.pi, sorry, _3.pi shows an example of this. So if I switch over to that code now, so let me close that down. So again, all exactly the same as before. The only thing I've changed the reviews that I've written here just to sort of demonstrate this a bit more, where we've got a little bit more of some sort of common bigrams here, like HSMA program, etc. I still create the count vectorizer exactly as I did before. I'm going to include stop words as I did before, but I'm also going to pass in another argument here called n-gram range, and I pass in a tuple here. Now, basically, what these two numbers in brackets represent, the first number is the minimum size n-gram we want it to pick up, and the second number is the maximum size n-gram we wanted to pick up, inclusive at both ends. So what this says is, I want you to look at both single words and words of in pairs of words. Essentially, that's the word I was looking for. So this will, you could just, if you wanted to, just look at pairs of words. You'd probably find that would lessen performance though, because you'd miss out. There'd be lots of things that aren't pairs of words, and you wouldn't want to sort of lose that. But you can do it however you like. So this would say, give me single word unigrams and also bigrams as well. We're looking at pairs of words. Everything else exactly the same as it was before. So let me run this and show you what will happen. So you can see our vectorization is a bit longer than it was before. So let me bring up the data frame so you can have a look, see what's happened. So here you'll see we've got some unigrams like 80s and brilliant, but we've also got some bigrams in here now. So we've got the combination of brilliant really and embraces 80s and HSMA program, which is the one we thought would come up. And the important thing to flag up is here, it will only include in the vectorization any two-word combination, two-word sequence that comes up in at least one of the documents. So it won't, if you were looking at every single pair combination, it will only show where it comes up in at least one of those documents. I think I mentioned everything there. Yeah, okay. So, bag of words seems like it's pretty decent. It allows us to create pretty simply these vectorizations, these numerical representations within vectors that are a fixed size, which we need if we're going to do things like machine learning with our text data. And it is true that a bag of words is very simple and very effective, but there are drawbacks to it as well. And you've probably already picked up what some of these drawbacks are. The first drawback that I sort of touched on earlier, it doesn't, because it's a bag representation, it's just taking that as a bag of random words. It's not capturing anything about the structure of the text. So you can't capture anything about the context. Now, context is hugely important for natural language processing, as we'll talk about all next week, and is the reason why things like ChatGPT now exist, because of this issue of context, which has transformed the world of natural language processing. And things like sentiment analysis are so much better when you can capture context. But as I say, we'll come on to that more next week. But for now, just understand you can't possibly capture context because you're just looking at an individual jumble of words, and they're not related to each other in any way in that representation. Also, any new documents that we add will likely contain some new words, which will then increase the size of the vectors that we create. Remember, they're all fixed size, so the vector for every document has to be, the size of the vector has to be the same, which means that if we add in a new document and it's got 100 new words, the size of all of our vectors, assuming none of those are stop words or we're keeping stop words, would then increase by 100. Okay, and that also paired with the third problem, which is if there are lots of words that are unique to just one or two documents, we're going to end up with something known as a sparse matrix. And a sparse matrix is basically this, where we end up with lots of zeros in our vectors. Zeros are essentially useless information, and it makes them very, very inefficient because we've got this huge matrix, and it's not really telling us much. It doesn't actually contain much useful information. It makes them really difficult to interpret. It slows down any processing and analysis we want to do with it. So it's not. You generally want to avoid sparse matrices. So it's a nice bag of words. Is a nice one to follow as a sort of simple introduction to the world of vectorization. But when you're doing natural language processing in earnest, you likely won't use it that much. You will use other vectorization approaches, though. Now, but I did mention, however, right back at the start, that one of the uses of using a bag of words vectorization is that we can look at how similar two or more documents are. So we can, in other words, if our documents are representing text, we can say they seem to be talking about the same kind of things. And that's quite a useful thing to do. And there's actually lots of different ways you can do that, perhaps unsurprisingly. One of the most popular ways, though, is using something known as cosine similarity. And it's basically a very popular approach for comparing the similarity of two vectors of numbers. And obviously, because using bag of words, we've turned our text data into vectors of numbers, we can use cosine similarity to identify the similarity of our two vectors, because we've now turned our text into vectors. So the advantage of taking text data, making it numerical, putting it in a vector, means that we can now tap into these kind of vector methods that we couldn't do if we just left them as raw words. So hopefully you remember vaguely, at least from school, that a vector is basically an object that has both magnitude and direction. And so in order to measure the similarity between vectors, we can measure the spatial similarity, because we can take any vector and represent it in multidimensional space. Now, obviously in here I'm showing two-dimensional examples, as always, so that it's easier to get your head around it. But again, the principles apply to multidimensional space as well. And what a cosine similarity will do is basically look at the angle between two vectors. Okay. Now, our vectors, it happens, represent text, but this applies to any vectors. You can use cosine similarity. And basically, our cosine similarity score will range between -1 and 1. Basically, values that are closer to 1 indicate the highest level of similarity between two vectors. Values closer to -1 indicate essentially the lowest level, because it indicates an inverse similarity. In other words, they are opposite one another, our vectors. So this is an example where we've got negative cosine similarity. Just to flag out, this can't happen if we're using, to generate our vectors, if we're using a count vectorizer, which bag of words is a type of count vectorization, because you're counting out how many times something occurs. In this case, how many times this word occurs in this document. That's known as a count vectorizer, sorry, count frequency vectorizer. Therefore, we can't have negative values, because there will be no negative values in our vectors. So this won't happen for bag of word representations. Can happen with others. And a value of 0 indicates that the vectors are neither similar nor dissimilar. So basically, for our purposes, anything above 0 indicates there is similarity, and you can pretty much interpret the value you get between 0 and 1 as being a kind of percentage of similarity. So the closer it is to 1, the closer it is to being 100% similar. So how do we calculate cosine similarity? Well, this is the equation, which looks scary, but actually is fairly straightforward. All this is doing here is just got some weird symbols. The top bit of this equation basically says you take the dot product of the two vectors. You'll remember dot product because we talked about it right back in the Python training, and I think we mentioned it a couple of times after. Remember, dot product is just where you take two vectors and you say I multiply the nth element of vector A with the nth element of vector B, and then you add up all those numbers. That is the dot product. That's all that is. So you take the first element of this vector here, multiplied by the first element of this vector here. So that's all that top bit's doing. It's just taking a dot product of the two vectors. The bottom bit is basically taking the magnitude, that's what these vertical bars mean, take the magnitude of each vector and multiply those two magnitudes together. The magnitude of a vector is actually very simple to calculate. You just take each value in the vector, you square it, and then you add up all those squared values, and then you take the square root of that final sum, and that gives you the magnitude of the vector. And so you do that for vector A, you do that for vector B, multiply those numbers together, and there's your bottom bit. So this looks scary, but it's really not. Dot product of the two at the top, and then calculate magnitude of A, magnitude of B, multiply them together. That's all that's saying. So then you take dot product divided by those two, the product of those two magnitudes. So let's just think for a really simple example. Imagine these are our two vectors. Vector A here, 0, 2, 1, 3, 5. Vector B, 1, 0, 1, 2, 5. Dot product, easy to calculate. First element of vector A times first element of vector B, so that's 0 times 1, plus second element of vector A times second element of vector B, that's 2 times 0, plus 1 times 1, etc., etc. So the dot product is 32. The magnitude of A is simply the square root of the first element squared plus the second element squared plus the third element squared plus the fourth element squared plus the fifth element squared, which comes out to the square root of 39, which is 6.25. Same for B, that comes to 5.57. And then the cosine similarity is simply the dot product, which is 32, divided by these two magnitudes multiplied together. So in this case, the cosine similarity of these two vectors is 0.92. In other words, they are 92% similar according to cosine similarity. That actually makes a lot of sense. If you have a look at those two vectors, they are similar. We can see they are similar. These are very easy to interpret because for each element of these vectors, the value is either identical or very close to it. So 0 and 1 close together. That's the one that's furthest away, the second one. But here, identical. The last one's identical. These are very close. So it appears these vectors are very similar, and cosine similarity indeed concludes that. Okay, any questions about either bag of words or cosine similarity?
I don't believe there are.
Oh, great, cool. That was nice and easy then. Okay, so what you're going to do now is you're going to go back into your groups. I'm going to give you until I think is this the last bit? I think it's the last bit. Yeah, okay. So I'll probably bring you back about 20 past, maybe 25 past. I'll see how you're getting on. Whether I want to give you more time just to... What on earth have I done here? Oh, there we go. Whether I want to give you more time to have a look at this. So you're going to go back into your groups. Basically, what you've been provided with, you've got 3 reviews for Back to the Future. What else? In 3 separate text files. In the repository, you've been given review 1, review 2, and review 3. These are just randomly plucked reviews from the ones that are in your that single text file earlier. I've just separated them out and given them to your separate text files. So the first thing, what I want you to do is to write some code that does this, okay? So I want you to, the code should read in the reviews from these files as 3 separate documents. Top tip, I think I've mentioned it before, but you know those wonderful things called f-strings, they're not just for print, you know, you can use them in anything that has a string, including a file name. So that might help you create a nice elegant solution for reading in the reviews that are called files that are called review 1, review 2, and review 3. Just a thought. Then I want you to vectorize the 3 reviews using bag of words. I want you to store the results of that vectorization in a pandas data frame. Then I want you to calculate and print the cosine similarity of the 3 combinations of pairs of reviews. So you've got 3 reviews, and you look at the cosine similarity between any 2, which gives you basically 3 combinations. So a couple tips for this, because you're probably thinking, well, hang on, Dan, You showed us the equation for cosine similarity. You didn't tell us how to do that in Python. No, I didn't. You can do this however you like. You could sit there and you could just write out the equation in Python code. That's absolutely fine. But a nice little tip, you may want to check this out, this little link here. There's a neat little way that you can apply the stuff you need for a cosine similarity equation in Python using NumPy. Hang on, Dan, we're not in NumPy, we're using pandas. This is going to spit out pandas. Yes, but you can create very easily a NumPy array from a pandas data frame using this simple command here. You just call on the data frame, whatever you've called it, dot to NumPy, and it turns it into a NumPy NumPy array. Sorry, I couldn't think of the term. It turns it into pandas data frame into a NumPy array. So that's handy, possibly, depending on how you want to do this. Once you've done all that, I want you to play around with it. Try including, excluding stop words. Does that affect the similarity scores you're getting out? Try including unigrams and trigrams, either exclusively or additionally. So think about the range thing that I was talking about. Have a look for other reviews or just other pieces of text that are more or less similar to each other. Basically, when we come back, I'll ask if anybody's found anything interesting, and there might even be some ad hoc PSG points up for grabs if anybody did find anything that looked particularly cool. But before we do that, before we put you into the rooms, I'm going to hand back to Sammy, who's hopefully got her judgment on your wonderful word clouds to reward some much-deserved PSG points.
I do indeed. So I'm going to award a couple of just quick bonus points first before I get on to the gold, silver, and bronze awards. Wanted to give Agnes 2 points just for your fantastic machine learning transcript word cloud. I think that deserves some recognition. TIA as well for 2 points for coming up with the fantastic game of word cloud, word cloud bingo as such, to trying to identify movies from the word cloud. That was a fantastic one. Pokey, I just want to give you a 2 point bonus as well. I believe you were the first group to post a masked image, so that deserves a little bit of recognition as well. Antic, 3 point bonus because you really persevered to get a really striking output. So there was a lot of effort that went towards getting that. So well done there. But now on to the main points. In bronze, we have Denise. I thought you did a really nice combination of mask and colours and a real group effort to get to that end result as well. Motorola and Zilog in joint silver. Motorola, yeah, fantastic, you know, some really nice outputs there coming out. You've come up with some really creative ones, and Zilog, you know, you came up with some very well, we can't not reward Chesney Hawkes, and really liked you using you know, comparing the two speeches from Johnson and Starmer in word cloud form. I thought that was a really nice idea. And finally, in gold, we've got Paula. How can I not, you know, reward the Barbie and Shrek and B-movie ones? That was some fantastic work there. Really nice use of colour and masking. So well done.
Fantastic, thank you, Sammy, and well done all. Yeah, really nice word clouds. And hopefully, if you haven't already, I'd encourage you all to check out each other's word clouds. Really nice stuff there. And I can't wait to see what more word clouds are generated. Although scarily, I fear there will be more about transcripts, and it'll just be large fonts of me going and which is basically just a typical Tuesday now. Okay, right. I'm desperately trying not to say I will now close down the. I've said it 100 times. Right, I'm going to stop talking. I'm going to open up the breakout rooms. I think that's safest for all. And I'll float around. Can't see what you wait to see what you come up with. Hi everyone. Okay, so welcome back. I hope you had fun with that. Most people seem to be getting on quite nicely with that. What was been really nice to see actually for both this and the word cloud exercise earlier is lots of people saying, "Oh, shall we try this?" That's a good thing to say. This is exactly the kind of thing. Follow your natural curiosity, and you know, if there are things in the exercises that you'd like to explore, absolutely do that, because you know, you are we are rapidly moving towards the project phase of the program where you're going to be starting to work on your own projects, and actually that natural curiosity is what's going to keep you going and exploring and sniffing out these different things. So I always say follow your curiosity on these things, and you'll learn and explore new things and find fantastic stuff. So, just before we close, did anybody find anything particularly interesting that they would like to share, potentially for Sammy to award you some points for sharing? Please feel free to just shout out. No.
Yeah, we tried comparing exactly same review files and see putting any parameters make it dissimilar. We got close where we would put one parameter, but it was 0.99999. I think that's just a
Oh
rounding.
wow. Oh, okay. So you were this was what was this with the Back to the Future review? Sorry, or
Yeah, we used the exact same file in in the list.
oh, I see. So kind of comparing it with itself.
Yes.
Oh, I see. Right. Yeah. That should be 100% similarity. So yeah, it's obviously just a weird way in which it's calculated.
Yeah, we just thought if we can break it, but
yeah. No, cool. I think a few other things popped in the chat. Anybody else had? Somebody said Dracula and Frankenstein are surprisingly similar. That's interesting. Unsurprisingly, not removing stop words increases the cosine similarity. Yeah, so obviously you would have probably found that if you left in stop words by default, which most people would have done, you would have found that the similarities are actually pretty good, pretty strong. But I guess you have to question whether it depends on what you're doing and what you're comparing. So obviously stop words are by definition common words that are found across lots of different pieces of text. So including them is going to increase the similarity. So I would argue probably for something like this, if you're doing this in earnest, you'd probably want to remove the stop words because you're not interested in that kind of it's kind of artificially inflating your similarity, because even if these things weren't similar at all, there would be some kind of similarity between them just through the fact that the stop words exist. So but yeah, really positive Back to the Future reviews, more similar to each other than oh, that's interesting. Okay, so people seem to love the same kind of things. When people don't like Back to the Future, they tend to disagree on what the things are that they don't like. That is interesting. I like that. I think that deserves some points. Of course, my argument would be that it's because people that don't like Back to the Future are incorrect and therefore don't have a cohesive argument. So that's proof, scientific proof that Back to the Future is indeed fantastic. I think that's what we've proven there. Comparing all the Back to the Future scripts against each other was also really high. Maybe yes. Well, I mean they are. It's basically one big film split into three. And there are certainly. I mean, there are deliberate bits where it repeats, of course, as well. So yeah, that is interesting. I like that that you've done that comparison of the scripts. You have some sort of quantifiable measure of that. Brilliant. Thank you. I think Sammy and I will award some points for those findings. I think that sounds really cool. Hopefully, have you got a note of those, Sammy? Just I'm conscious we'll lose the chat until tomorrow. If have you got those?
Yeah, I'll make sure to screenshot those before we leave.
Excellent. Thank you. Fantastic. Okay, well, thank you very much. Thank you, everyone, for today. Hope you've enjoyed it. So we had the machine learning final machine learning session this morning, and then natural language processing this afternoon. Next week, it's a full day of natural language processing. We'll look at name density recognition in the morning, and then in the afternoon, sentiment analysis. All I will say is that if you are a fan of a particular pirate-themed point-and-click adventure game, you are going to absolutely love the sentiment analysis session. I will say no more other than to say it is, as the clues have come through from the Ghost Pirate LeChalk, I've gone all in on that. So hopefully what will be a very fun session for all of you. There are a massive amount of PSG points up for grabs. We're talking triple figures next week. So lots and lots of possibilities. We'll be using your sarcastic reviews, and then the following week is the week where there will be over 200 PSG points available. So everything could change still for this thing that you're competing, and we haven't decided what you're getting. Okay, great. I hope you've enjoyed today. Hope it was a fun session. Look forward to seeing you all next week. We'll post instructions hopefully tomorrow about what you'll need to install for next week, but it'll just be the same kind of stuff as you've had before, so it shouldn't be anything too complicated. I will stop talking. Chris and Stuart have identified what the theme might be next week, so do tune in and make sure that you join them. I may have even changed the music for the intro, so just bear that in mind. Awesome. See you next week, everyone. Bye bye.